Okay, this is the second part of the Unit 1 Matter and Measurement Notes. And we're going to focus on kind of scientific method and experimentation in this section. First off, scientific notation. And scientific notation is when your numbers are in this format. Something times 10 to the something. We use scientific notation for really, really big numbers or really, really small numbers so that we don't have to write in all the zeros. So you'll have something like 2.2 times 10 to the 14th. This is a positive exponent, which means the decimal point would be moved to the right, so that would represent a really big number. This is a negative exponent, so that means the decimal point would be moved to the left, so this would represent a very small number. Basically, what you need to be able to do is punch scientific notation into your calculator and do calculations with these exponents. Most of you have probably learned to use the caret key, and that works fine, but sometimes that runs into some issues. So the EE key is actually the preferred button on your calculator to punch in scientific notation. So, again, you need to be able to punch scientific notation into your calculator. If you don't know how to do that or you want to learn how to use the EE key, let me know and I can show you that very quickly. Okay, scientific method. Somewhere along the line in your school careers, in your science classes, you have learned the 3 or 4 or 5 steps to the scientific method. I am not concerned that you know the steps to the scientific method. I will not ask you, what's step 2? I'm concerned that you understand that good science is a process of experimentation and that there is an actual process method to be followed. So, when you decide to test something, first thing you're going to do is make your hypothesis, which is your educated guess. I think when I do this, this is what's going to happen. So you make your hypothesis. Then you develop an experiment so that you can test your hypothesis. You do the experiment and you look at your results and you draw conclusions. It might be that your hypothesis was supported. It might be that your results tell you your hypothesis was wrong. It doesn't really matter. Either way is okay. Sometimes you learn more when unexpected things happen, your results don't seem to match what you thought would happen, than you do when your hypothesis is right. So, once you get your conclusions, then you might be done, or it might be that that leads you to develop a new hypothesis, a new experiment to test some more. The idea, again, is that you understand that there is an actual process, that good science has a procedure for testing, that you follow this scientific method so that you're doing good science. Let's look at a little bit more at this experiment piece, the designing an experiment to test your hypothesis. When you're doing an experiment, you have variables. If something is a variable, that means it can change. So variables are the things that can change in your experiment. You only ever want 2 things to change. You want to see the effect of, if I change X, what's the effect on Y? Okay, so if I change this, what's the effect on that? Those are the only 2 things you want to be looking at. So the independent variable is the one you change deliberately. You set how it changes. And the dependent variable is the one you measure the result for. So let's say that you want to test the effect of the angle of what's called a plane, kind of like a board, on the distance the ball rolls. When you do that, what you're going to set is the angle of the board, the plane. Okay, here you have it kind of flat, you make it a little steeper, you make it a little steeper. So angle of the plane is the thing that you are changing, so that would be your independent variable. What you're going to measure is how far the ball rolls, the distance the ball rolls, so that would be your dependent variable. Those are the only 2 things you want to look at, so anything else that would affect how far the ball rolls has to be held constant. And those are going to be known as controlled variables. Anything else that could change during the experiment, but you want to hold it constant. So, if we're looking at our ball and plane example, you want to see the effect of changing the angle on the plane, compared to how far the ball rolls. That means things like the surface will have to stay constant. If you do it on gravel one time and carpet the next time and hardwood floors the next time, then something other than just the angle is going to affect how it rolls. So you'd want to keep the surface the same. You would want to make sure you use the same ball all the time. The same plane all the time. All those kinds of things that could change, but that you want to hold constant are controlled variables. So the independent variable is the one you're changing, the dependent variable is the one you're measuring, and those are the only things that should be changing. Everything else should be a controlled variable, be the same every time you do the experiment. When you get your data, you're going to evaluate it. You're going to get a bunch of numbers typically. There are lots of relationships that can exist between numbers. Sometimes no relationship exists. We're going to look at two in particular, direct proportions and inverse proportions. Direct proportions means as one variable goes up, the other one goes up. This is the idea that the higher the angle goes, the farther the ball rolls. Okay? So that would indicate that it might be a direct proportion, and the way you're going to tell that for sure is if you divide the variables, it gives you a constant. The opposite of that is an inverse proportion. And inverse means opposite. So the idea here is that as one variable goes up, the other one goes down proportionally. And the way you're going to test to see if something is an inverse proportion is that multiplying will give you a constant. So let's look at an example so that this makes a little bit more sense. You get this data. You want to see, you have a balloon that at different volumes, different sizes, you want to see how much pressure there is. So when the balloon is 5 liters, the pressure is 10 atmospheres. When the balloon goes down to 2 liters, the pressure goes up to 25 atmospheres. When the balloon goes down to 1 liter, the pressure goes up to 50. So when you look at this data, you would initially think that it might be an inverse proportion. As this one's going up, 10, 25, 50, the volume is going down 5 to 1. So as the pressure increases, the volume decreases. As one goes up, the other one goes down. That leads you to believe that it might be an inverse proportion. The way that you're going to test that is by multiplying. We said if it's an inverse proportion, multiplying will give you a constant. 10 times 5 gives you 50. 25 times 2 gives you 50. 50 times 1 gives you 50. So each time you multiply, you get the same number. That's what we mean by a constant. Multiplying gives you the same number over and over again. So yes, this is an inverse proportion. As the pressure goes up, the volume goes down. When you multiply across, you get the same number every time. That your clue, it's an inverse proportion. Direct proportion would be the opposite. As the pressure went up, the volume would have gone up. And the way you would test for that is dividing would give you the same number over and over again.